This is a server that can service multiple clients with one thread. Yes, this is different from many server implementations that have one thread per client. We're going to be using the Java NIO library to implement non-blocking sockets using selectors, channels, and buffers. If you aren't already familiar with how regular sockets work in blocking mode, I'd highly recommend you check out this video that goes into how blocking sockets work. But without further ado, let's write some code. So to start, I already have some boilerplate code here that resembles what we looked at last time we did socket programming with blocking sockets. That code doesn't really look any different from the perspective of the main class here. We're creating a scanner over system.in, and then we're going to have multiple versions of this program. One version is going to be running a server, other version is going to be running client 1 through n. That's where we know whether we're going to create an instance of our server versus our client. And then for the clients, we also do pass in system.in to make sure that as the client, I can input information that then gets routed to the server, and then the server can respond back to the client in some way. For a quick refresher on what this port number is, think of it as a sub-address within the context of IP addressing. So I've got an IP address that indicates the main address of a packet that I'm going to send. And then the port number indicates which particular port within the physical server I'm going to address. So think of it as like a unit within an apartment complex or something like that. So to start, let's go ahead and populate the start method of our server implementation. And currently there's no implementation in here, so we're going to fix that. Let's make a try with resources block. So the first thing we're going to put in here is we're going to instantiate a flavor of server socket, except this time it's going to be a server socket channel. A channel is something that's part of the Java NIO library that we'll get into here in a little bit. So I'm just going to call this server socket channel, if I can spell here, equals server socket channel dot open. So open is going to open the default server socket channel. We don't really need to customize this very much. We're going to go ahead and bind it to an inet address later on, so we don't need to worry about the port number or anything yet. And then we also want to open a selector. And the selector is going to get interesting because the selector is the real magic behind how we can make our server single-threaded. But we do have an error here, and that is that both of these open methods can throw IO exception. So let's catch IO exception. And then we're going to wrap in a runtime exception just so we can move on. Now we're going to do 3 different things to our server socket channel. The first thing is that we're going to put our channel into what's called non-blocking mode. This in essence is going to make it such that if I read or write to that socket, it's not going to block, which is a little bit weird when you first think about it, but we'll get into what that means here in a bit. The second thing we need to do is we need to bind to the inet sock address that we're going to use within our program. And then the third thing we're going to do is we're going to register our channel with the selector. So let's get into that after we write a little bit of code here. So server socket channel dot configure blocking false. Server socket channel dot bind new inet sock address port number, and then server socket register with the selector, and now we need to have a selection key. So what are all these different selection keys? So how a selector works is that it's something that runs within a thread, and what it's doing under the hood is it's running system calls to pull different resources. If you're familiar with kernel level coding, you might be familiar with pull, or you might be familiar with reading data out of a file descriptor. In the end, a socket is typically a file descriptor. The important point to make here is that when I am reading data from a socket, there are multiple ways I can do that. And when I am running pull on the operating system, I can either block when that happens, or I can return early depending on if there's some event that was posted that indicated that I'm ready to get data again. Multiple different ways of programming, and this API is exposing that. So there are multiple different things that we can have our selector monitor, and that's what these are called out as here. You notice that these are all bit masks, meaning that we could have multiple of these being monitored at any one time. The specific one that we want to have being monitored right now is operation except. And if we follow the source code to operation except, we can see here that it is socket except operations. So a selection keys interest set contains operation except. If the selector detects that the corresponding server socket channel is ready to accept another connection or has an error pending, then it will add to the keys ready set. So basically what this line of code is doing right here is when the server socket channel has an accept operation ready to be processed, my selector is going to fire. Can you already see how we're going to write this code? We're going to have a loop which waits for events on the selector, and when the selector receives an event, then we're going to do something with it. If you're familiar with lower level programming, that would involve something like interrupt handling, and you have this big while loop where you just wait for an interrupt to fire. This is a similar type of concept. And the selector is the one that's going to tell us when we are ready to process something. So let's go ahead and make that loop. I'm going to loop forever, and I'm going to say selector.select. So the select method here currently does not have any sort of timeout. It's going to wait indefinitely. So while my server socket channel is in non-blocking mode, technically the select method here still blocks. So we're not really preventing blocking entirely within our server. We're just choosing to move where the blocking happens. Instead of having every single read or write from every single socket that we create, which is n number of sockets when we have n clients, we have a single selector that has to block waiting for an event on the selector. But first, I really should be guarding this. The reason I'm doing this is because if you look at the documentation of the select method, it returns an integer. The number of keys, possibly 0, whose ready operation set now indicates readiness for at least one category of operations for which the channel was not previously detected to be ready. If you're familiar in lower level programming with the concept of spurious wake up, that's essentially what I'm preventing here. To be honest, I haven't looked at the code of the select method in the JDK to determine if it could return 0 if I don't have a timeout included in here. But past experience tells me that I should be careful when I am calling something like this to always check if I'm returning something I'm looking for, and if I'm not, I'm just going to continue on and I'm going to block again. So now that I know I have keys to process, I'm going to iterate over the keys, like so. And now one thing I do have to do at the end, which is a little non-intuitive for first users of this API, is I need to do selected keys, and I really need to clear them all. The reason for that is because when the Java NIO library came out, it was based off of JDK 1.4, which was pre-enhanced for loops, and a lot of times while loops were used with iterators. The standard idiom when using this was an iterator, and you would remove the element at the iterator when you were done grabbing a reference to it, so that by the end, you basically had gone through the entire list and you had cleared it all out. The idea of this selected key list is that we only remove from it. We don't add to it. If we were to add to it, we would get an exception thrown. I think it's an unsupported operation exception. But point being, we need to make sure that when we're done with our selected keys, we clear all of them out so that we don't have stale data next time the select method gets called and returns. Now that we've written the skeleton code for the selectors, a lot of this is going to start falling in place. We're going to write some code to be able to accept connections. Then we're going to be reading data from our clients, and then we're going to send data back to our clients. Do be sure to stay tuned though, because there's some weird things that go on with ByteBuffers that we'll get into here in a little bit. All right, so now this for loop is what we need to do next. Whenever I am entering this for loop, I know that I have selected keys, and I know that how it should work is that the only keys that I'm getting are those that are tied to this accept operation. But let me go ahead and check that. So I can check that via key that is acceptable. The key is going to be considered acceptable, aka is acceptable returns true, only if the key is pointing to an accept on a socket. So now I need to make sure that the channel that this key is pointing to is something that I'm aware of. So I can say if key.channel instance of server socket channel. And just a reminder on what this is doing right here. Instance of is going to check for a null value, and then it's going to check for whether the value that this variable is pointing to right here is of this particular instance. So it can be either a server socket channel or any subclasses. And this channel here indicates the variable name for the server socket channel instance that my key.channel was downcasted to. Basically, this prevents me from having to add another line of code in here, which is doing the actual casting. It's just a shorthand, which is nice to limit extra characters. All right, now that I have a channel, I know that it is a server socket channel, and I know that it should be ready to do an accept. Let's go ahead and accept it. Let's do channel.accept. Just like what we would do within blocking sockets, we're now going to accept client connections. Except this time, the accept method is not going to block. And the reason is because this key is telling us that we are ready to accept a connection. And we don't execute this for loop until the selector actually indicates that there's something to read from. So channel.accept here should not take very long at all. Let's go ahead and call this our client. And now we have sockets and we have port numbers, we have INET addresses, all the stuff that we're used to with blocking sockets. Now we're going to take the socket object and print some information to the user. So let's make a variable called client info, and then we'll use string templates. Let's see here, we want to do socket dot get INET address dot get host address, and then let's go ahead and put in another variable, which is socket get port. Then we'll indicate here via another string template. We'll say connected, and then we'll print out the client info. And the next what we want to do is actually going to look very similar to what we have a little bit higher in the code. And that is we're going to configure blocking as false for this new client connection. And then we're also going to register this client on the same selector. So let's do client.configure blocking false. Client.register, the same selector, and now we're going to use a different selection key. This time we're going to use the read key. Now if you look at the documentation for the read operation, if the selector detects that the corresponding channel is ready for reading, has reached end of stream, has been remotely shut down for further writing, or has an error pending, then it will add the read operation to the keys ready operation set. Okay, so that was a mouthful, but point being, when my client now has something that is ready to read, whether it has actual bytes on the client socket or whether it's an end of stream or something like that, then the selector is going to notify me. So cool. If I switch back to my server, I shouldn't really have to change any code because my selector is now going to select on either accepting another client connection or when my client connection that I have here gets a read access done on it. Sweet, we're getting a lot closer here. Now, one thing that IntelliJ is asking me here is selectable channel used without try with resources statement. And that is a good point. Channel.accept is now creating this socket channel object, which is what client is right here. This is what the IDE is telling me, and I'm not closing it. Should I be closing it? Yeah, probably. But I don't know when I'm done with my client other than when I know that I'm done with my server. Maybe I could say when I do a end of stream, I'm done with it. What I think I'm going to do instead is I'm going to collect all of my clients in a hash set. And then at the very end of the program in a finally block, I'm going to go ahead and close all those resources out. So let's write some of that code. All right, after we have registered our client with the selector here, we have now added it into our set of clients. When we are all done with our program, we attempt to close down all of our clients. And the IDE is asking me, should you really be throwing an exception within a finally block? I'm actually glad it's asking me because this is a little known fact. If you throw an exception and your finally block throws another exception, then the original exception that gets thrown just disappears entirely. So it's actually pretty difficult to debug things. So you really only want to do this if you really have to. And the fact that I have a close that I'm doing here that could throw a checked exception, I could instead just print the stack trace here rather than throwing another exception, but I kind of feel bad doing that. So I'm just going to propagate the exception up. And if the close is also throwing an exception, then I think some really bad things are happening. All right, now to get to the client here. One of the big differences between the server and the client in this particular application is that the server is the one that really needs to worry about resource constraints. Because when I add 1,000 clients over here, I don't want to have to create 1,000 threads. I only want to have one thread, which is going to wait on that selector. Over here on the client, if I'm in blocking mode, I don't really care that much. Maybe you have clients that need to be a little more conscious of that, but the client in my case, I don't really care, so I'm not going to worry about configuring my client for non-blocking mode. But I'm still going to use NIO socket library to demonstrate the difference between blocking versus non-blocking mode. So let's do a try with resources, and we're going to call it socket, and it's going to be a socket channel. Open. Again, we need to catch IO exception. And then we need to wrap it in a runtime exception. I'm actually going to rename this to server channel to make it a little clearer what this channel is referring to. And I want my server socket channel to connect to an inet socket address. And then kind of like the server, I'm going to make a while true loop. And then I'm going to say scanner.next line. We're going to set that equal to line. And then we're going to say if line is not quit, we're going to continue on. Otherwise, if it does equal quit, we're going to go ahead and break. We have a server that should be accepting multiple different client connection attempts. And then we have a client which establishes the connection, and then it reads data from the scanner but doesn't do anything with it yet. Let's go ahead and take a look at how it runs. Yes, this is my server, and this is my client. All right, so we have an established connection, and then our server indicates localhost port 52512. Let's go ahead and run another client here. Cool, connection established. We'll see that the port number is different on that second client. Awesome. So now the cool thing is that on the server side, we only have one thread that's going to handle all these different client connection attempts. I think it's pretty cool that we can scale the number of clients, yet in theory still have one thread that maintains that selector. The key, if you're thinking ahead, is that that selector thread should really not be doing very much. If it has to do any sort of heavy lifting, that should be offloaded to a different thread. But the nice thing is that just because you're a server and you're doing a lot of operations on all these different clients doesn't mean that all of them are very heavy lifting commands, if that makes sense. So still, this method has a lot of benefits with the single-threaded model versus the heavily multi-threaded model, which has a lot of context switching involved with it. So now this is where the fun begins with ByteBuffers. And we're now going to read and write from ByteBuffers. So what is a ByteBuffer, you might ask? Well, you could think of it as essentially an object which captures an array of data. The array could either be something that is in heap space or it could be in native space. The array that we're talking about here is going to be in heap space. I'm going to allocate it from a Java perspective. I'm not going to deal with the really low-level optimization of native backing of a ByteBuffer. But some folks do look at that when you need to be really performance critical. I'm not going to worry about that for this application. So to start, we're going to make a buffer. It's going to be ByteBuffer.allocate. And we're going to throw in 1024 bytes. Why did I allocate exactly 1024, you might ask? Well, I'm glad you asked. 1024 is a power of 2. It's 2 to the 10th power. Similarly, you could choose 512, 4096, 65,536. It really doesn't matter. The point being, it's a power of 2. That's a convention that's been used in code for quite a long time when you allocate buffers of data like this, where you use a power of 2. Because in older CPUs, it is a lot more efficient to do that. And even when you talk about newer CPUs, when you talk about smaller blocks of contiguous memory, it's quite efficient to allocate in powers of 2 because that's how memory is laid out. When you talk about larger areas of memory like 1024 bytes, 2048 bytes, things like that, at least I'm not aware of any significant reason to do it. I just do it more out of convention because that's kind of often what you see in code. Now that we've allocated our ByteBuffer of 1024 bytes, now we're going to do some different operations on it. So the first thing we want to do is we want to set it up to be able to read data into it. So what I want to do with this line variable is I want to add on the new line character. I'll get into why here in a little bit. But really what I need to do is I need to make this line variable go into the buffer. And how I'm going to do that is, well, first I want to call buffer.clear. This puts my buffer into a good state at the top of every time that it is used within the while loop. And the ByteBuffer API is pretty nice. I can chain multiple method calls together. So I can use the put method, and I'm going to use line.getBytes. And now what this is going to do is this is going to write the bytes from my line string that I get from user input into the ByteBuffer. And then I want to do something called flip. Flip is basically the way that you can easily convert a ByteBuffer into thinking that it is in read mode versus write mode. When I am reading data into the ByteBuffer, aka I'm writing to the ByteBuffer, I'm going to want the ByteBuffer to start at a particular position, and then I write the bytes in order. When I want to read from the ByteBuffer, I need to reset the position of the ByteBuffer of where I'm reading from, and then I want to read the data that I just wrote out. So if I were to not call flip, then the ByteBuffer is going to try to read out data at the last index from where it just did the write, and that doesn't make a lot of sense. So that's why I have to do this flip here. Now I'm going to actually write the data. Buffer.hasRemaining. Now we're going to write to our server channel from the ByteBuffer. The reason that we are wrapping the write here within the hasRemaining is more out of caution. A write should be writing all of the data out of the buffer that is there, especially because we are in the blocking mode. But it doesn't hurt to make sure that there's no extra data in the buffer when we are done with the write. So we basically make sure that we don't have any remaining data to write to. All right, so now our client is writing data to our server. And now what we need to do is we need to update our server. So we have the list of keys here, and we're checking to see if our key is acceptable. What happens if we get a read operation ready to go? Is acceptable is going to return false to that. So we need to add another case. If key is readable. And then we're going to have similar code that we did up here, where we need to make sure that this is a key that we are aware of, except this time, the key needs to be a socket channel. Actually, one other thing I should do here, I'm going to say unknown channel. I want to do this same thing in both spots with the accept key or with the read key, because what's happening is if we get an accept on a channel that isn't a server socket, that's not good. And if we get a read on something that is not a socket channel, then that's also not good. So now what we want to do is we want to read some bytes out of our client. I'm going to rename that here. Client.read. And now I need to read this into another ByteBuffer. So let's go ahead and define that right here. I'm going to say buffer equals ByteBuffer. Allocate, we'll use 1024 again. Okay. Remember how I mentioned that we could get a read key triggered if we have no data to read from? That would be indicated by bytes read equals -1. And when that happens, then we're going to say disconnected, and I want to include the same client info that I have up here. Actually, I'll copy both of these. And I will need to get the socket object out of here. So I'm going to say socket equals client.socket. And then instead of connected, we want to say disconnected. And then let's do client.close. And then now we can safely remove it from the client hash set. All right, so now we know there's actual data within the buffer. So let's read the data out of the buffer. First, we're going to flip it so that we are flipping between the read and the write on the buffer. And now we're going to convert the bytes from within the buffer into a string. We're going to say new string. I could say buffer.array. That's going to give me the array that's backing this buffer. Now I want to get the buffer's position, which after I call flip, it should always be 0, but I'm just going to be a little bit safe here. And then I also now want to get bytes read. I could choose to also include the encoding of the bytes here, such as UTF-8. The reason I'm not doing that is because in the client code, when we are getting the bytes from the string right here, that's also using the default character set, which is UTF-8 on most systems. So I don't need to really define that in this case, but if you were not in control of the client code, you should know what character set you are interpreting your string bytes as, just as an FYI. Let's go ahead and print out the data. And then at the end, just to be good stewards, we really should be clearing the buffer again, because flip is going to leave it in a state thinking that it only has a certain number of bytes to read or write. So let's clear it back out and make sure that we can do a read or a write on it again. Let's go ahead and take a look at the code and see what it's doing. Yes, this is the server. And no, it's not the server, this is a client. Hello. Excellent. So we can see our hello string is now over on our server. Is this working still? Yes, it is. Perfect. Yep. All right. Now, one thing you'll notice is that I have these extra new lines here. That is because it added the new line character after I grabbed the string from each of these inputs. So why did you do that? That doesn't really make a lot of sense here. Well, I'm glad you asked. Let's go ahead and dig into it. So my client code is blocking sockets, meaning that I'm going to block until this write is done, and I've cleared the write output buffer, and I know that when I am done with this while loop that there's no more remaining data within the server channel's write. However, the sockets in here, all of these are non-blocking, meaning that if I have a indication that I can read some data out of my client buffer, let's say that I have an indication that I can read 40 bytes of data. So bytes read equals 40. That 40 doesn't necessarily indicate the entire message that the client sent me. It only could be part of it. And you might start seeing this when you have larger messages. So this is a really key thing to think about when you're writing code around non-blocking sockets. You gotta make sure that you write your code in such a way that it might take multiple iterations through your while loop to get the entire set of code that you're looking for. Meaning that you might get the results within your socket read in chunks. And I'm not really addressing that here. In fact, I'm causing an issue because I'm gonna print line. If I don't want to print a line every time that I get an incomplete read, I only want to print literally what is getting sent to me, I really should just be calling print, because then I'm not going to add any extra new line characters at the end here. So instead, now what this is going to do is it's going to literally print raw what it gets. If I were to have a really, really long string, maybe you could see it print out in chunks on the command line, but it's probably not going to see in this particular example because I have a system running on localhost, so you're not going to really see it, but just trust me that it is very easy with non-blocking sockets to have situations where you only read chunks of the data, and because read doesn't block, it only reads in what is currently available in the output buffer. Awesome. Our server is receiving data from our clients. Let's go ahead and now respond back to our clients with the data that the server receives. So now to do full cycle, let's make our server an echo server and echo back the message that it received from the channel. So after we print out the data that we receive, we're going to have similar code that what we have in the client. While the buffer has data remaining, we're going to do client.write buffer. That's honestly all we have to do. This code is going to take the data that we already have in the ByteBuffer, and it's going to write it out to the client, and it's going to do it in, again, chunks, because this is a non-blocking socket. So the write will only be what's currently available within the buffer, because flip will get the buffer in that state. But again, it's better to be cautious, especially with non-blocking operations, to wrap this in a while to simulate blocking to make sure that you've got everything through that's in the buffer. And then now in the client code, we have to read the data that we got from the server as part of the echo response. So we're going to say bytes read equals server channel.read from the buffer. But before we do that, we need to clear our buffer. The reason is because we just did a write And we thought that we wrote all of the data that was in the buffer, meaning that the buffer, even though 1024 bytes were allocated, the only actual data available to the buffer was the data that it needed to write. And I want to clear that out. I want the entire buffer to be able to be read into again. So I'm going to clear it out. And then now we're going to mark bytes read here again. If the server messes up and sends us fewer than 0 bytes, I'm not really going to handle that right now. So I'm just going to say if bytes read is greater than 0. Let's go ahead and flip the buffer again. And then similar to what we have within the server code, we can copy over the data that we get within the buffer's array at the current position after we flip the buffer, bytes read, and then we'll print it out here. The one difference here being that I want to make it clear that this came from the server. So we'll do that, and then we'll say server. Let's run it again. Hello. Hi, server. Cool. Then if we add a second client, let's make sure that looks good. And I will hide my camera here. Nope, this is a client. Another client. Yo. Excellent. This looks like it's working as expected. So now we're done, right? Well, not exactly. There is one additional thing I want to talk about, and that is we're talking about byte buffers. So we're talking about individual bytes. One detail that's often glossed over in the context of introductory networking is endianness. Endianness is the way that you interpret the order of bytes when you have multi-byte values. So think about an integer. An integer within Java is a 4-byte value, aka 32 bits. And the reason that I need 4 bytes of information to encode an integer is because in Java, an integer can have 2 to the 32 different options, which encodes 32 different bits, aka 4 bytes. And when I'm the computer, when I'm reading a 4-byte value, how do I know if this first byte indicates the most significant portions of the integer, aka what makes it a billion, or whether it's the least significant, meaning that it's the values that make it like 2 or 10? The answer is it really doesn't unless you standardize a way to indicate the endianness of your system. So really, there are 2 main types of endianness, little and big. So on my operating system at least, it is little endian. However, when you're writing networked code, the default you should use is big endian. So that poses a problem. If your operating system code thinks it's supposed to be in little endian, but the networking code thinks it's supposed to be in big endian, you can have this situation where the values don't agree for multi-byte values. Java fixes this to a degree in that all Java code implies big endian, even on a little endian operating system. That doesn't come without its issues, but we'll get into that here in a second. First, I just want to show what endianness is with some examples. So in my server, instead of writing out this buffer of data like this, I'm going to get a little more interesting. And I'm going to put an integer value in here equal to bytes read. And then I do need to flip it again here. So what's going on is I'm going to put an integer value in indicating the number of bytes that the client sent me. And now within the client here, I do have to rewrite this a little bit. So after I flip the buffer, I'm going to say read data equals a new byte array of bytes read. And then I can do buffer.get read data. Basically what this is going to do is that's going to read the data from the buffer into the byte array. And then now instead of the server just printing out data, I want to do arrays.toString of read data. And then this one will be buffer.getInt at index 0. So the difference here is that this first variable that we're going to print out is going to be the bytes as we are reading them out from memory from the server. Then the second one is going to be the interpretation of those bytes as an integer. It'll make a lot more sense after I run the code. Let's go ahead and do that. All right, so I've got a client and a server up. If I type hi, the server here returned 0004. So 4 indicates that I sent 4 characters over, because again, this is UTF-8 encoding, meaning 8-bit encoding, meaning that each character in a string is 8 bits normally. So why are there 4 bytes here? I thought I'm only sending 2. Well, the first one is H, the second one is I, and then a new line character within Windows is 2 characters. It's a carriage return and a new line feed. So HI, carriage return, line feed. So that's 4 total characters. And then we have our byte array here, which represents integer value 4, because again, an integer represents 4 bytes in memory. And in this case, we're using BIG ENDIAN because this last byte here, which is the least significant byte, has the least significant impact on making this value change significantly. Let's make this interesting. We're going to have our server write the data as little endian, but our client is going to not specify the endianness, aka it's going to use big endian. To do that within our server code, we're going to do buffer.order byte order.little endian. The byte order class has little endian, big endian, and native endian in it, where native endian refers to the endianness of your operating system. Native endianness might be useful if you are skipping heap buffers and you're using a native buffer for performance reasons. But in general, Java's default is big endian. So now let's switch our byte order back, and then we'll say byte order.big endian, just so that we don't change any of the other code. Let's go ahead and try this now. All right, so now we're gonna use the same string, and whoa, okay, now we got something very different going on here. You'll notice that the byte order is reversed. And that is really important because now our client is completely misinterpreting the size of the data that we're sending over. If you remember, that 4 used to be over here in our least significant byte. It is now in our most significant byte, which is why that most significant byte has a significant impact on the size of our integer. I hope this proves to you that endianness is something that is really important to get right, and you can't just assume that the other end is going to follow the byte order that you are necessarily. You should always ask the question on what is the byte order of my operating system, and or what is the byte order of the data that's going to get sent to me. The good news is that in the context of networking, the default network order that people should be sending you data in is big endian, but you still gotta check. Hopefully you enjoyed that walkthrough of writing that single-threaded server implementation. If you did, please do smash that like button. I'd really appreciate it. However, if single-threaded isn't really your jam and you want to continue going with a multi-threaded server path, I'd highly recommend that you check out multi-threaded servers using virtual threads. A virtual thread is a lightweight alternative to OS, or what we call platform threads, that enable servers to scale much better. If you haven't already, I highly recommend you check out my video on virtual threads, or really any of the other videos I have on multi-threading in general, because let's be honest, it's a pretty complicated topic. Thank you for watching. I hope you have a good rest of your day, and I hope to see you next time. Take care.